In this video, we're taking a look at quadratic modelling. Now, for quadratic modelling, we're not really learning anything new here. What we're essentially doing is just recapping the skills that we've previously learned, such as completing the square, solving quadratics, and sketching quadratics. But we're looking at this now in context, so we're modelling situations with quadratics. So what we can see here is we've got a javelin that's thrown over even ground from a platform. The height in meters of the javelin above the ground after t seconds can be given by this function, or it's modelled by this function, okay? And then we've got two parts to answer here. So part A, we just want to give an interpretation of this constant, 1.98 in the model. And in part B, we're asked after how many seconds would it take for the javelin to hit the ground using our given model. So let's start with part A here. So how do we interpret this constant here? Well, what I'm going to do is I'm just going to write our quadratic again in the form of ax squared plus bx plus c, or in our case it would be at squared plus bt plus c. Okay, so that's going to be minus 2.38 t squared plus 7.98 t plus 1.98. Okay, and I think it makes it a little bit easier to see what this 1.98 actually represents here. So if we think about this now, I've got a quadratic here. Remember, this constant term at the end gives us the y-intercept, because if we set t equal to 0, the quadratic term here is equal to 0, the linear term here is also equal to 0, and we just get left with this constant. Now, we don't want to just say that this is the y-intercept, we need to give this in context of our model. So what we're looking at here, well, this is the height in meters of the javelin above the ground after t seconds. So there's two ways to kind of word this really. Either's absolutely fine. So one way I could word this would be to say that this is the initial height in meters from which the javelin is thrown, or we could say that this is the height of the platform, okay, from which the javelin is thrown. Either of them is absolutely fine, but you just need to make it clear that this 1.98 is the initial height, okay? So I'm not going to give the interpretation here, but do make sure that you write something down here. So just say 1.98 represents the height in meters of the javelin being thrown, the initial height from which it's thrown. Okay, now this will only ever be 1 mark, so I wouldn't worry about this too much. But obviously, that is a mark that we do want to get. But like I said, you don't need to put too much for that. Okay, so that's part A. Now for part B, we're looking at after how many seconds did it take for the javelin to hit the ground. So once the javelin hits the ground, what we're saying though is that the height is equal to 0. Okay, if it hits the ground, the height is equal to 0. So what I'm doing then is I'm taking my quadratic function here and setting that equal to 0. So what we're saying is minus 2.38 t squared plus 7.98 t plus 1.98 is equal to 0. Okay. Now, this is a negative quadratic. So if you think about the sketch of this, what you're going to get is actually two solutions. Okay. It's my x-axis. This is my y-axis. We know the initial, or the y-intercept here, which would be our initial height from which it's run, is 1.98. So if I just sketch this here, it might look, say, something like that. Okay. So that's 1.98. Now, like I said, we're going to get two solutions here because we get this solution. We also get this solution here. But we're just looking for after how many seconds did it take for the javelin to hit the ground. Well, clearly, the condition here is that t is greater than or equal to 0. So anything to the left of our y-axis here, we omit. Okay, so we don't need anything to the left. So what we're looking for is just this point here, okay, where it hits the x-axis. Now, it's up to you how you go about solving this, whether you use the quadratic formula, whether you complete the square. That would be a really nasty way to do it. I wouldn't complete the square. You could if you really wanted. Or whether you just put this into your calculator. So what I'd say here is just put this into your calculator. Assuming your calculator does have the function to solve polynomials like this. So if I just put this into mine here, so obviously make sure you assign the correct values for A, B, and C. So A would be minus 2.38, B would be 7.98, and C would be 1.98. And if you enter this correctly, you get two solutions like we said. You get x1, in my case, is equal to 3.58500, and so on. And then I also get x2, which is equal to minus 0.232, 0.59, and so on. Okay. Now, like we said, we only want one solution here, and we want the positive solution. Okay, that means it's to the right of the y-axis. In that case, we don't want this solution. Okay, so we don't want this solution here. So give that across, but we do want this one. That's our correct solution, but we have to be careful. We want to give this answer to 2 decimal places. So therefore, the time, which is in seconds here, would be 3.59. If we give that to 2 decimal places, so t is equal to 3.59 there. Okay, so after 3.59 seconds, the Javelin hits the ground, okay, using our given model. And there we have it, so that's our solution to the first question. This next one here is a little bit longer, so again, we've got the context. So we've got a company that makes a particular type of calculator. The annual profit that is made by the company is modelled by the following equation. And notice here we've got this quadratic equation. It looks a little bit funny, but this is a quadratic. If you was to expand this here, then we'd have an x squared term. So we've got a quadratic. We're told P is profit measured in thousands of pounds and X is the selling price of the calculator. So using the model, we need to explain why £16 is not a sensible selling price. Now, if we're just told to explain why £16 is not a sensible selling price, then all we'd assume here is that we just need to substitute £16 here into our model. Remember, X is the selling price, so what we're saying here is X is equal to 16, okay? But what I want to do here is substitute X equals 16 into our equation here. And what we'd assume then, if this isn't a sensible selling price, is that we get a negative profit, okay? So P is equal to 120 minus 2.5 times, so that's 16 there for X, so 16 minus 8 all squared, okay? And all we need to do here now is just put this into our calculator, so let me just do that. So I do 120 minus 2.5 lots, so that would be 8 squared there, 8 squared. And what I get here now is a negative value. So I get minus 40 here, okay? So remember, this is in thousands of pounds. So what we've got here is a negative profit. So clearly £16 is not a sensible selling price. So P is less than 0. So therefore, negative profit. So negative profit and £16 is not sensible. Okay, that's all we really have to say there. We just need to show that we get a negative profit. Okay, so there we have it. So that's the solution to part A. Now for part B, we're given that the company made an annual profit of more than £100,000. Okay, we should have a pound sign there. Let's just put that in there. So we need to find, according to the model, the least possible selling price for the calculator. Okay. So what we're saying here is, what's the least possible selling price such that we make an annual profit of more than £100,000? Well, the formula here for profit is given by this equation. So what we need to do now is set this up as an inequality. So what I'm saying here is our profit, 120 minus 2.5 lots of X minus 8 all squared, must be greater than 100. Okay, remember this is in thousands of pounds, so we just set this greater than 100 rather than 100,000. Okay, so just be careful for that. It's really easy to make that mistake. And what I want to do here now is just solve this inequality. So what I'm going to do first, I'm just going to subtract the 120 off both sides. So I get minus 2.5 lots of X minus 8 all squared is greater. So 100 minus 120, that gives me minus 20. Okay. And then what I'm going to quickly do here is just get rid of all this over here, just so we've got enough room. We finish part B off. There we go. We should have enough room. So let's carry on solving this inequality here. What I'm going to do next is divide both sides by minus 2.5. Now be slightly careful here. Remember, when you divide by a negative value and we've got an inequality, then the sign flips. So once I divide by both sides by minus 2.5, on the left hand side I get X minus 8 all squared, and the inequality flips. So this now, rather than greater than, will be less than. Okay, and minus 20 divided by minus 2.5 gives me positive 8. Okay. And finally here, we can square root both sides. So I'm going to get x minus 8 is less than plus or minus the square root of 8. And it's up to you how you kind of go about this, whether you take it from this quadratic here, or whether you go from here. So x is less than, and then take the 8 across. But what we get here, if I just do it up here, is x is between. So what you're looking for here is where is the quadratic less than. Okay, so what I'm going to get then is a minus root 8. That would be the smallest value. I also get a plus root 8. Okay, that's what I'm saying for my inequality. That's my solution for my inequality here. Okay, so I don't want to confuse. Let me just get rid of this line here, just so I don't confuse. But that's what we're saying from here. Okay, so once you solve this quadratic inequality, this is what we get, right? Now, this is a range of values, so any of these values within this inequality will satisfy this condition. Okay, but we're looking for the least possible selling price. So the least possible would be this value here. Okay. Now, put this into your calculator and see what you get. So if you do a minus root 8, what would that give us? Well, let me just put it in myself. So a minus root 8, that would give us 5.171,572, and so on. But the issue here is, we're looking at money now. So obviously it's sensible to round to 2 decimal places. But we've got to be slightly careful, because if I round this to 5.17, then this is actually below this value, okay? So what that means, we need to round up to 5.18, okay? If I round this to 5.17, this inequality does not hold, and as a result, we wouldn't have a profit of more than 100,000. It would be just short, okay? It might be something like 99,500 or something like that, but it will be short. So in that case, the least possible selling price, write this down, the least possible selling price is equal to £5.18, okay? And a good thing to do here is just to substitute this value now, this x value here, back into our equation, okay? And if you sub this in, you'll notice your value, or the profit here that we get, is just over 100,000, okay? So it seems sensible. We've got a profit of more than 100,000. Everything looks good, okay? But there we have it. So that's our solution to part B, okay? For part C then, we're told the company wants to maximize their annual profits according to the model. What will be the maximum possible profit? Now, this one's actually quite straightforward once we just kind of think about this a little bit. So for my profit here, notice I've got 120 minus 2.5 times this squared term. So it doesn't matter what value of x we substitute in here, whether that's positive or negative, this will always be greater than 0. Okay, it will always be positive. So the issue here is I'm doing 120 minus 2.5 times a positive number, so we'll always be subtracting something from the 120. So in that case, just have a think about this now. How would I actually get the maximum profit here? Well, in that case, the maximum profit would just come from when this part is equal to 0. Okay, if we can set this equal to 0, we do 120 minus 0, which would give me a maximum possible profit of £120,000. So what we get then for the maximum possible profit is £120,000. Okay, that's the maximum possible profit. And then in part D, we're asked to find the selling price that gives the maximum possible profit. So part C and D basically go together. So we're saying now, what do I need to set x equal to here to get 0? So minus 2.5 times x minus 8 all squared. Well, how do I set this equal to 0? Well, in that case, we just need to make x equal to 8. Okay, we make x equal to 8, and then I said 0, but if we make x equal to 8, then we get 8 minus 8, which is 0. 0 squared is 0, times that by minus 2.5, and again, we just get 0. So therefore, the selling price will be £8. Okay, so selling price is equal to £8 there, and that gives us the maximum possible profit, okay, which is £120,000. That's the solution to the second question. Moving on to the very last question here now on quadratic modelling. Now this question looks pretty similar to the very first question that we did, and what we've got here is an archer who fires an arrow, and the height, h meters of the arrow above the ground, is modelled by the following formula. And notice here for h, we've got a quadratic equation. Okay, so this is an example now again of quadratic modelling. We're told d is the horizontal distance of the arrow from the archer measured in meters. And then we're told that the arrow travels in a vertical plane until it hits the ground. So 3 parts here. Part A, with reference to the model above, interpret the constant 1.65 in the model. So very similar to the first question that we did, where again we were just interpreting the constant. So if we take a look at our model here, and notice we've got our quadratic equation, what I'm going to do here is just rewrite this so that it's in a form that's more familiar to us. So my quadratic term will come first, then my linear term, and then my constant. So it's going to be minus 0.005 d squared plus 0.3d, and then finally plus 1.65. Okay, so that's our quadratic. Now again, this constant here at the end, we notice that if we set d equal to 0 here, then this quadratic term will be equal to 0. This linear term here will also be equal to 0, and we just get left with this constant. So what does this constant represent? Well, it's just the y-intercept, but we need to be careful here. We don't want to just say it's the y-intercept. We want to give this in context of our question. So the context here is the archer firing the arrow, and the height h meters of the arrow above the ground is modelled by this formula. So this 1.65 here represents the initial height in meters from which the arrow is fired above the ground. So we just need to say something along those lines. I won't write out here in full, just to save time, because it's already quite a long video, but just make something along those lines. So again, all you need to say here is basically that the constant here, 1.65, represents the initial height in meters of the arrow above the ground, or from where it's fired. Something along those lines is absolutely fine there. Okay, again, that's only 1 mark, so you don't need to worry too much about that, but that's all we need to put for part A. Now for part B, we're asked to find the horizontal distance travelled by the arrow as given by the model. So the horizontal distance travelled will be when it touches the ground. So if I imagine just sketching this quadratic here, that's my y-axis, this is my x-axis here. So this is going to be a negative quadratic, so we've got this N-shaped parabola here. It's going to look, say, something like that. It's not perfect, but it is just a quick sketch. And that would be our constant term here is 1.65. That's the initial height from which it's fired. And notice here, this arrow keeps going until it touches the ground here. Okay, and that would give us the horizontal distance. Okay, this distance here. Okay, so let's just do that in a different color just to highlight that. So we're looking for this distance here when it touches the ground. Okay, now what we're essentially looking for here is the solutions to this quadratic. Now, like we can see from our sketch, we're actually going to get 2 solutions, and we saw this on the first question, but clearly we're going to omit the negative solution. Okay, anything to the left of the y-axis here, we don't want that. Okay, again, d is greater than or equal to 0. So we're only going to take the positive solution here. So just back to our original pen color. So all I need to do here now is take my quadratic, so minus 0.005 d squared plus 0.3d plus 1.65. And we just need to set this now equal to 0. Okay, we're looking for it crosses the x-axis, so that will be when this quadratic here is equal to 0. And from here, again, it's completely up to you how you go about solving this quadratic, whether you use the quadratic formula, whether you complete the square, or whether you use your calculator. So I'm just going to use my calculator here. That's absolutely fine. You get full marks for doing it, and it just saves time. So putting this into your calculator, obviously make sure A is 0. or minus 0.005, B is 0.3, and C is 1.65. So if we do that correctly, then what we get here is 2 solutions. I get x1, which is my positive solution, so I get 65.07135, and so on. And then I also get x2, so this is my negative solution. We're going to omit this, but I'll write it down just so you can check that you've got both of these solutions. So I get minus 5.07135, and so on. Okay. Now, like we just said, we don't want this negative solution here. That's to the left of the y-axis, so we don't want this one here, so we'll give that a cross. But we do want this solution here, this positive solution. So that's the distance, but let's give this to a sensible degree of accuracy here. So the horizontal distance travelled by the arrow, as given by the model, so this will be d in this case, If we give this to one decimal place or three significant figures, this will be 65.1. And we measured here in meters for the horizontal distance, so 65.1 meters there. Okay, and that's all we need to do for part B. And for part C here, we're asked to write our quadratic here in this form. Now, this looks a little bit different, but hopefully you actually recognize that this is just simply completing the square. So what I'm going to quickly do here is just clear the screen just so we've got enough room to do part C. So we want to complete the square on our quadratic. So the first thing I'm going to do here is I'm going to take my quadratic and write it in the form that we're more familiar with. So the quadratic term comes first, so minus 0.005 d squared plus 0.3d, and then finally plus 1.65. Okay. What we want to do here now is get this quadratic here into completed square form. Now, remember, when we're completing the square, we need the coefficient of our quadratic term here, so the coefficient of d squared, we need that to be equal to 1. Now, at this point here, clearly that isn't true. We've got our coefficient being minus 0.005. So what we need to do here to start with is factor out this coefficient. We factor this out. So we take the minus, let's get rid of that. We don't want the d there. We factor this minus 0.005 out, like so. What that's going to leave me then with is d squared. So this 0.3 here, that's the same as dividing that by minus 0.005. So I just do that on my calculator. I get minus 60d there, or minus 60d. And then 1.65 divided by, again, minus 0.005. And that gives me minus 330. Okay. Now, because our coefficient of d squared is 1 in this case, we can now complete the square on this quadratic here. So keep the minus 0.005 on the outside for now. We'll multiply through at the very end. So completing the square here, we're going to get d minus, divide the coefficient of d here by 2, so that'll be d minus 30. We square this bracket, and now we subtract this value squared. So what's minus 30 squared? Well, that would be 900, but we subtract this off, so we've got minus 900 minus 330. Okay. All we want to do now is simplify this square bracket here. I get minus 0.005. The d minus 30 stays as it is, all squared. So that stays as it is. But this minus 900, so minus 900 minus 330, that gives me minus 1,230. And what we need to do now to finish here is multiply through now again by this minus 0.005. So we're going to get minus 0.005 lots of d minus 30 all squared. And now we need to multiply minus 1,230 by minus 0.005. So minus 1,230 times minus 0.005, and that gives me 6.15. And that's positive because we got a negative number times another negative number, we get positive. So plus 6.15. And we're pretty much done now. Let's just make sure we write it in this form here. Okay, so notice they've got a minus b times d minus c all squared. What we've got here is minus b times d minus c all squared plus a. So we're pretty much there. Let's just write in the correct form. So we do this up here just to finish with. So clearly this a here will be minus 6.15. So we get 6.15 minus 0.005 lots of d minus 30 all squared. And from here now we can clearly see the values of a, b and c. In that case, a is equal to 6.15. b is this 0.005 here. 0.005 here. And then finally c will be my 30 here. And there we have it. So like you can see, it's very easy to make a mistake here, but it is just completing the square, but the numbers are pretty tricky to work with. It is very easy to make a mistake, like we said. But remember, all we need to do is factor that minus 0.005 out, and then we can complete the square like we normally would, because the coefficient of d squared is equal to 1. But there we have it. That's our solution, and that's what you should get for part C. So let's just highlight that. That would be your solution here, 6.15 minus 0.005 times d minus 30 all squared. And there we have it. So that brings us to the end of this video on quadratic modelling. In the next video, we're going to take a look at exam revision for quadratics.